Hello, I'm Minjung Lee. I'm gonna start my presentation. Actually, I'm not processing my personal research now, so I will present the related research and my research plan. I'm interested in the text-to-image generation task, so I will explain it with the paper I read recently. Text-to-image generation is a technology that receives text information as input and generates an image corresponding to the text. The text-to-image study began in 2015, demonstrating the potential to generate new visual sentences with text given the image capture condition. In 2016, we used GAN instead of VAE to improve the accuracy of images and showed that this system can not only generate good level of objects but also enable zero-shot generalization. There has been so much progress in the field of text-to-image generation since 2015. But limitations are also revealed, such as object distortion, non-realistic object location, and objects that do not mix well with the background. For text-to-image generation, it is often evaluated using a relatively small dataset, MS-COCO or CUB200. There is a text-to-image generative model research paper solved using large-scale datasets because the size of these datasets or models may be a limitation of existing approaches. Therefore, the goal of this paper is to learn the proposed autoregressive transformer. The proposed model has 250 million transformer image text pairs with 12 billion parameters. And the authors showed that if a super large model is trained using such large amounts of data, it can generate high-level images that can be controlled by a natural language sentence. This model makes text and image tokens into single streams. But there are two problems here as well. Using the image in pixels is bound to cause memory problems. Also, models that use likelihood star as the target function tends to prioritize short-length dependencies between pixels. So, to solve these problems, the model's learning method consists of two main steps. In stage 1, the DVAE encoder and decoder are learned through the compression restoration process of the image. The input image of 256 by 256 is compressed into 32 by 32 image tokens, and the reconstructed image is learned to be similar to the original input image. This method can make the input token sequence of the transformer small without significant loss of quality. If you look at the above example image, you can see that the details of the input image are lost little by little, but the overall restoration is very well. Therefore, Stage 1 can be the process of preparing the text token embedded value to generate the desired image through the DVA decoder. And through this compression, visual quality may be maintained while compressing the context size that the transformer has to process by 192 times. The encoder works to reduce the spatial resolution by 8 times. Details, for example, the texture of cat hair writing, thin lines are partially lost or distorted, but the overall characteristics of the image are still recognizable. In the paper, a large vocabulary size of 8,192 was used to minimize the loss of information. Next, in stage 2, the DVAE learned in the first step is fixed and the Prio transformer is learned. 256 text tokens and 1024 image tokens compressed into DVAEs are concatenated. This way, one data stream is created and the joint distribution of text and image tokens are learned by learning the autoregressive transformer. The overall learning process can be interpreted as a process of maximizing the evolution lower bound (ELB) for the combined probability distribution of image X and caption Y, and token X for encoded RGB images. As you can see from the figure below, the qualitative findings according to experiments, the proposed model has the ability to construct unusual concepts with high level of abstraction. In addition, the model can understand the degree of dependence between words in a sentence through the ability to generalize combinations. To explain, there E is shown to solve the text-to-image task even in a direction that was never expected. In addition, it seems that some complex generation was possible, but inconsistent result was derived for this test. It was found that image-to-image translation was also possible within a certain degree of reliability. The last slide, my research plan. Just as the performance was improved using zero-shot learning in the corresponding model, I'd like to find and study ways to improve the current limitations in the learning method or perform text-to-image generation task more efficiently. The more objects there are, the less trust will see problems such as not being able to express the relationship between objects well, recognizing spatial roles, and omission when creating captions. I'd like to conduct research to supplement this area. Thank you for watching my presentation.